We have seen that an edge dislocation can glide only in the slip plane containing the dislocation line and its purchase vector. Also, we have seen that a screw dislocation can cross slip from a given slip plane to another slip plane. However, an edge dislocation cannot cross slip. But for a certain conditions, edge dislocation can move out of the slip plane onto a parallel plane directly above or below the slip plane. And this process of moving out of edge dislocation out of its original slip plane is called as dislocation climb. And we'll be seeing this process, dislocation climb, for an edge dislocation. So let's consider this edge dislocation where this is an extra half plane and this is our slip plane. So let's mark this edge dislocation over here and let's mark the slip plane also. This edge dislocation moves to another slip plane above or below by assistance of vacancies, and these vacancies are thermally equilibrium defects, and these vacancies form at high temperatures or elevated temperatures. So let's understand this process first. Let's see the influence of vacancies on it later. So let's consider this edge dislocation where there is an extra half plane and here it is a slip plane. And let's create a vacancy over here. And now the atoms from this extra half plane can diffuse into this vacancy, and it diffuses here, and you can see that a dislocation has moved up. You can see an extra half plane here and this is our slip plane. So you can say that the dislocation has moved up, or this moving up is called as climb or climbed up. So this process is called as positive climb or a climb up. Now, as you would have guessed it, if there is a positive climb or a climb up process, there must be a negative climb or a climb down. So let's consider that too. So let's consider this edge dislocation and this is our slip plane, and let us have vacancies over here. Now in this case the atoms will diffuse to the extra half plane and other atoms will start diffusing in, and you can see here an extra half plane, the atoms has diffused and you can see a dislocation has moved down here because this is an extra half plane and this now becomes our slip plane. So you can see that a dislocation has moved out of the slip plane onto a parallel plane which is directly above or directly below it, and this process is called as climb. This process is particularly called as a negative climb or a climb down because a dislocation is moving down. So the climb is a process of dislocation moving out of the original slip plane onto a plane which is parallel above it or below it. So this process is called as climb. Now you can say that here in this process there was a removal of row of atoms. You would have seen that we have created a vacancy and the atoms from an extra half plane moved to those vacancies, and thus we can see that there is a removal of row of atoms. Here in this case you have addition of row of atoms to an extra half plane. We have seen that the atoms moved to extra half plane. Thus, in other words, we can say that there is decrease in vacancy concentration when there is a positive climb or a climb up. You have seen that there is a vacancy which was created and atoms from an extra half plane move to that vacancy, and thus the vacancy concentration must decrease here in this case when there is a positive climb of an edge dislocation. While in this case there is an increase in vacancy concentration, and that is visible from the schematics where you can see that the atoms move to an extra half plane and thus creating a vacancy, or there is an increase in the vacancy concentration when a dislocation climbs down. Now you can say that we have seen the process of climb up and climb down with an assistance of vacancy. As you know, vacancy is an equilibrium defect. What do you say that there is always a thermally equilibrium concentration of vacancies which is already present in a material, and that is given as Nv upon N naught equal to exponential of minus Q upon Kt, where Nv is number of vacancy, N naught is total number of lattice points, and T is an absolute temperature, Q is activation energy to form vacancy, and K is Boltzmann constant. As you can see that vacancy is thermally equilibrium defect, that means there is always an equilibrium concentration of vacancy. So how this vacancy concentration is decreasing or increasing? I can say that how there is a change in the vacancy concentration, and how is that it is assisting an edge dislocation to move on to another slip plane to climb up or climb down. So you can see that this equilibrium concentration of vacancies can be affected by an application of stress. So when the material is stressed at a given temperature, there will be a change in equilibrium concentration of vacancies, where sigma is an applied stress and omega is an activation volume. So when I apply tensile stress, the concentration, the equilibrium concentration of vacancy increases, and thus by changing the stress state there will be change in the concentration of vacancies, and this concentration of vacancies will help an edge dislocation to climb up or climb down. Now when I consider this relation, this sigma omega, this term is much smaller than Kt, which is much smaller than Q, which is an activation energy to form vacancy. But if you consider this term sigma omega upon Kt, which remains, let's say, 0.1, and if it is in tensile in nature, the stress applied, this Nv, that is number of vacancies, it increases by 10% if this term is just 0.1. So you can see an effect of this stress, applied stress, on equilibrium concentration of vacancies. As I mentioned you that we have an equilibrium concentration of vacancies, let me write it down. So we have vacancies, I will write it here. We have vacancies, and that is assisted by temperature. And at what temperature? At what temperature this becomes important? So the temperature greater than 0.4 Tm of, that is melting point of an UR alloy. So you have vacancies, the concentration of vacancy increases when the temperature is more than 0.4 Tm, and thus, let me write it down again, the climb become important at elevated temperatures, and it is also called as thermally activated process. So climb generally occurs at high temperatures, or it is an high temperature phenomena. High temperature, I mean by temperature more than 0.4 Tm of an alloy, and this Tm is always Let me write it down here also. The Tm is always measured in Kelvin. So number of equilibrium concentration of vacancy increases with temperature, as using this relation you can find out. And this concentration of vacancy is also affected by an applied stress. And if it is tensile, you can see that there is an increase in the concentration of vacancies. So this is a process called as dislocation climb, where an edge dislocation moves out of its original slip plane onto another slip plane, another parallel slip plane above or below. And this is thermally activated process assisted by vacancies, and this process is only occur for an edge dislocation. Now let's move on. So now we have seen three processes: glide, cross slip and climb. Now let's compare what are typical observations from these three processes. So let's say we have shear stress along Burgess vector. So there can be a glide, and there are dislocations like screw and edge dislocation. So they both can glide when there is a shear stress along its Burgess vector. So glide happens on a given slip plane. Now when there is a shear stress along Burgess vector, there can be a cross slip, and we have seen the cross slip can occur only for an screw dislocation. And normal stresses will cause climb. We will see this how normal stresses result in climb. So normal stresses causes climb, and climb occurs only for an edge dislocation. So now let's say glide and cross slip. So these two processes can be influenced by Chrysa's system, applied stress and temperature, while climb is thermally activated process and occurs at high temperatures, temperature greater than 0.4 Tm, as I mentioned you earlier. And diffusion here plays an important role because vacancies are being created and atoms has to diffuse into those vacancies. Thus diffusion play an important role. So there is a climb up and climb down process where we have seen the vacancies concentration increases or decreases. Thus when climb process occurs, it can act as a source and sink for vacancies. The glide and cross slip is called as a conservative process, and climb is called as a non-conservative process. What is conservative process here? Here, when a glide happens, there is no change in volume. But when climb occurs, we have said that it is a source and sink for vacancies, and thus there will be a change in volume when climb occurs. So there is a change in volume. So here when I say conservative, I am talking about volume is conserved. And thus climb is a non-conservative process and glide or cross slip is a conservative process. Now let's understand when dislocation moves, what is a plastic strain generated. We have seen all these processes. Now let's find out actually what is a plastic strain generated when dislocation moves. So for that, let's consider this crystal which has dimensions length, height h and d is width. And let's consider these are the slip planes which has these dislocations on these slip planes, and they move on this slip plane along D, and which these dislocations has Burgess vector B, and let us apply shear stress tau, and this dislocation moves along D in this direction, and causes a plastic strain. Let's say it creates a plastic strain in this fashion by creating a step. So we can figure it out what can be an overall plastic strain by the moment of these dislocations together. So let's consider this height. This will be the height h, and this will be a displacement, total displacement which is being created. So this is height h. This is a total displacement. I call it delta. So this is a total displacement, and this delta is much less than h. That is the height of this crystal. Now we can find out what is a shear strain. Let us call that gamma, and we know that the shear strain we can define it as gamma is equal to delta upon h, because delta is much smaller than h. So we define shear strain as to be gamma equal to delta upon h. Now let's consider this total number of dislocations to be n. And let's say if a dislocation moves an entire distance, let's say any dislocation moves an entire distance d, it creates a step by magnitude b, because the displacement vector is b here, that is, which is a Burgess vector. Now let's consider a general case where dislocation moves a distance by x amount, it creates a step by magnitude delta. Now this delta, we can find it out. Delta is equal to b upon d into x, because when dislocation moves an entire distance d, it creates a step magnitude of b. So delta is equal to b upon d into x. Now if let's say an dislocation moves by distance xi, it creates a step delta I, and this delta I can be written in a generalized form, that is delta I is equal to bd to xi. Now this total displacement can be written in terms of delta I, and this delta will be summation of all this delta I for n dislocations. So we can have a summation from I to n bd into xi, which is nothing but this delta I steps. So now we have got what is a total displacement. So we have total displacement, and this b upon d is constant, so I can take out of this summation term, and I can write it as bd summation of I to n xi. Let me divide it by n, that is number of dislocation, and multiply it by number of dislocation. So you can get this term as to be an average x, or average displacement on this glide planes. So this is our average displacement of dislocations on glide plane. And I have this delta. Now I can find out a shear strain. So I have delta, I plug in this value in this equation, and I multiply and divide it by its length, and I can see that this ln is nothing but a total length of dislocations. So I have this relation, I rearranged it in this fashion, and I can say that this ln, because I have n number of dislocation, and the length of the crystal will be the length of dislocation line, so it will be the total length of dislocations, this ln. And you can see that LDH is nothing but a volume of a crystal. I call it as Vc. So I can write it as gamma equal to LD B upon Vc to x bar. And this LD upon Vc, that is total length of dislocations per unit volume of crystal, is nothing but the dislocation density. And I can replace it LD upon Vc by dislocation density times Burgess vector into an average glide distance for for dislocations. So as we can see that these dislocations are moving and contributing to shear strain, and we are considering that all dislocations are moving and contributing to shear strain. But there are dislocations which don't move in a crystal and they remain sessile, or these dislocations which don't move and don't cause a plastic strain, these dislocations are called as sessile dislocation. So I need to modify this relation, and I modify it in terms of the dislocation density by rho m, where rho m represents a mobile dislocation density, that is dislocation which are mobile or free to move or which are not sessile. So I get a relation that gamma is equal to rho m b x bar. So this relation which we get based on a moment of a dislocation over a distance t in a crystal. Now let's understand this relation in more detail. So we have gamma, which we have related with a mobile dislocation density, a Burgess vector, and average glide distance. Now we can differentiate this relation with respect to time, because as most of the dislocation processes or deformation processes, or most of the deformation processes occur for a given time. So we can differentiate this relation with respect to time, and we can consider that rho m and b remains constant for that given length of time. So this cannot be valid for most of the processes, but let's assume that rho m, that is a mobile dislocation density, and b, this remains constant. So we differentiate this relation with respect to time, d gamma upon dt, and we differentiate this average glide distance with respect to time, assuming that rho m to be constant, and we can write this as, because this was a shear strain, so this becomes a change in shear strain with respect to time as a shear strain rate, and this becomes a velocity of dislocations, and average velocity of dislocation. So we can find a relation between shear strain rate is equal to mobile dislocation density into Burgess vector into average velocity of dislocations. Now we have seen this for a glide of dislocation. Similar relation we can develop using a climb of dislocations. Now let's do that. So let's consider this crystal with height h having n number of dislocations, and you have a climb strain which is developed as delta. This will be a normal strain which will be developed because dislocation will climb up and climb down, so this will be a normal strain. So I can write it as this strain equal to delta upon h, which will be change in length upon original length. So epsilon I can write it as delta upon h, where same assumption, delta is much smaller than h, and thus I can find out this epsilon to be equal to rho m b x bar c, where rho m is a mobile dislocation density and x bar is an average climb distance. Similarly, if I differentiate this relation considering or assuming rho m to be constant, I can get a similar expression where strain rate I can correlate with rho m, that is mobile dislocation density, into Burgess vector into average climb velocity of dislocations. So here xc bar is average climb distance and vc bar is an average climb rate of dislocations. As we know that we have seen climb requires jumping of atoms, because there is a creation of vacancies and atoms has to jump into those vacancies, and that climb process involves this jumping of atoms. Climb is much difficult than glide. However, climb becomes active or dominant when there is an increase in temperature, as it is a thermally activated process. And as temperature increases, the VC, that is average climb rate of dislocation, also increases. So we have seen by dislocation glide or climb, we can find out a relation between strain, dislocation density, Burgess vector, and average glide distance. Similarly, for a climb process, we can find out a relation between the strain, with here it remains a normal strain, into the normal strain equal to dislocation density, mobile dislocation density into Burgess vector, and average climb distance. And similarly, if you differentiate this relation, we can find out a relation between strain rate in terms of dislocation density, Burgess vector, and average velocity of dislocations for both glide and climb of dislocations. And these kind of relations are called as Orowan equation. With this, I will stop here.